All right, let's dive in. Today we're tackling a really cool question. How do computers, which only really get numbers, actually make sense of human language? We're going to explore a core idea that powers so much of the digital world you use every day. I mean, seriously, have you ever stopped to think about it? When you type a question into a search engine, or your music app suggests a new song, how on earth does it get the meaning behind your words? It feels like magic, right? Well, it's not magic, it's just some really brilliant math. And this isn't some abstract, theoretical thing. This tech is working for you constantly, every single day, from the search engine that just gets what you're looking for to the spam filter that keeps your inbox sane. It's all about one thing: comparing pieces of text to see how similar they are.
So, how do we build that bridge between our words and their code? Well, the answer, as we're about to see, is to turn language into something computers are incredibly good at: math.
The very first and absolutely crucial step is something called vectorization. Don't worry about the term. All it means is we have to translate our messy, nuanced human words into clean, structured lists of numbers. We call them vectors that a computer can actually work with.
Okay, so let's break that down. We're going to start with a simple but super powerful method to see exactly how this transformation from words to vectors really happens.
We're going to use a technique called the bag of words model. Now, don't let the name throw you off. The concept is incredibly simple. We literally treat each sentence like a bag. We just toss all the words in and count how many times each one shows up. We completely ignore grammar, word order, all of that stuff.
Okay, let's get our hands dirty with an example. Here's our sentence A. Data science is amazing. Nice and simple.
And our sentence B is machine learning and data science. So you'll notice it shares some keywords with the first one, data and science, but it's obviously a different sentence.
Now, the very first thing we do is create a master list. You can think of it as our combined dictionary of every single unique word used across both sentences. This list is going to be the blueprint for our vectors.
And here's what we get. Take a look at the vector for sentence A. We just go right down our master vocabulary list. Does it have the word data? Yep, so we put a 1. Does it have science? Yes, another 1. How about machine? No, so that gets a 0. We do this for every word for both sentences, and just like that, poof, our words are now numbers. They're officially vectors.
Okay, so we've got our vectors, the text is translated. Now for the main event. How do we actually compare them? This is where the real fun begins.
We use a measure called cosine similarity. Now, the key idea here, and this is really important, is that we're not measuring the distance between these vectors, we are measuring the angle between them. It's like asking, how much are these two ideas pointing in the same direction? And what we get is a beautifully simple score that's always between 0 and 1. A score of 1 means they're pointing in the exact same direction, a perfect match, and a 0 means they're completely unrelated, so it's super easy to interpret. So, how do you get that score? It's basically a 3-step recipe. First, you calculate something called the dot product. It's just a single number that captures how the vectors relate to each other. Then you find the length or the magnitude of each vector by itself. And finally, you just divide that first number by the product of the other two. That's it.
And for our two sentences, the final score is 0.707. That's a really strong match. Which, makes perfect sense. Both sentences were clearly about data science. We've just mathematically proven that these two ideas are closely related. Now, this is so much more than just a neat math trick. This simple calculation is a cornerstone of how we analyze text, and it powers countless things we use every single day. Let's just look at a few.
I mean, from organizing news articles into topics, to powering search engines,
catching plagiarism, recommending your next favorite movie. All of these systems depend on this fundamental ability to measure how similar two pieces of text are.
So, why the angle? Why not just measure the straight line distance between the vectors? Well, this is the key advantage. Cosine similarity doesn't care about the length of the document. A short article and a massive research paper can still be a perfect match if they're about the same thing. Distance-based methods would get thrown off by that difference in length.
Here's a perfect, practical example for you. Your spam filter has a library of what known spam emails look like, all represented as vectors. When a new email comes in, it's instantly converted to a vector, and the system just checks the angle between it and the spam vectors. If the angle's too close, it gets flagged. Simple, but incredibly effective.
Okay, so after all of that, what's the big idea you should walk away with? Let's bring it all home. It's really important to know that what we just did is a foundational concept. Today's AI systems use way more sophisticated ways to create these vectors. Things like BERT and Word2Vec can actually capture context and nuance, so the word bank would get a totally different vector in riverbank versus investment bank. But the core principle of comparing those vectors with cosine similarity, that remains exactly the same. This quote really just says it all, doesn't it? This technique is the bridge. It's what allows us to take messy human language and apply powerful, quantitative, mathematical analysis to it.
At the end of the day, that's what this is. It's an elegant and surprisingly simple way to put a number on the relationship between different ideas.
And that really leaves us with a final, fascinating thought. If we now have a way to mathematically measure the angle between ideas, what other complex human concepts could we begin to quantify and understand? What's next?